No, kitty, you don't want breakfast? All right, I'll close the door. You won't stay in here with me, Hammy, okay? You'll let your mama sleep. Come over here, bud. All right. Good morning, gang. Today, as discussed last week, we're going to continue talking about power series. In particular, I am going to show you how to apply calculus operations to power series today. So the main goal for today's lecture is to discuss integration and differentiation of power series. But before we get there, I want to address a few things. So let's do it. This, of course, is section 2 of Calc 2. It's a lecture, and it's the 9th of November, 2020. I've graded some of your exams, but not all of them, so I haven't released the exam grades yet, but you'll see those dropping later today when I finish up the rest of your class. So far, they are about what I would expect, which is to say they're not perfect, but I don't expect perfection. This is one of the harder parts of the entire calculus sequence. Calc 1, 2, and 3. Exam 2 and Calc 2 is generally the hardest, the worst. So kudos to those who put forth a true, honest, serious effort. I will be doing my best to give everybody as much partial credit as I possibly can as we go through this. What else do we need to talk about preliminarily? Shit, I felt like I had another announcement. I don't think so. Okay, yeah, so exam grades will be out a little bit later today for you guys. Today.
When does the study guide get put in?
Oh, yeah, good question. So you guys and 3 of my other classes had exams last week, and the last round of those exams, I set myself a deadline to have them graded by Wednesday. So I will be doing exam grading up through Wednesday, and then after Wednesday, I'm going to go back and do study guides. That's also when I'll be grading any of the like makeup exams or exams that were done at a weird time, or if you weren't able to submit your written work the regular way, if you had to email it to me because of some technical problem and couldn't get it to submit on Canvas, all of that stuff will be done after Wednesday. So yeah, study guides will be graded probably by Thursday, as will be any like makeup or extraneous circumstances exam 2s. Yeah, so Thursday for study guides. Today, we continue in 11.9 with integration and differentiation of power series. I thought maybe before we do this, it would be worthwhile to look at one problem from 11.9, kind of last week's style, because we will be continuing to use that technique today. So is there any particular problem from last week's homework that you guys would like to look at from homework 10? My last class all really wanted to see 21 and 22, but I'm happy to do whatever you guys would like. Okay, so I'm just going to do one of those two, same as I did for them. Any strong feelings between 21 or 22? Okay. So I remember it well enough, but just to be certain. So here. This is something like x cubed over 1 plus x squared or something like that. X squared over x to the 4 plus 16. Okay. So this is homework 10, problem 21. We want to find a power series for the function f of x equals x over x to the 4 plus 16. X squared over x to the 4 plus 16. All right. So 21, 22, very similar. They all require the same sort of thing, namely the geometric series trick. So recall. This was the primary thing we talked about last time. The geometric series trick is just that 1 over 1 minus r is sigma n from 0 to infinity, r to the n. Right? This is what we use as our jumping off point for all of the homework problems last week that asked you to find a power series. So my goal is to write this function in this form. And the way I would begin is by saying, well, f of x, I can pop the x squared out. That's x squared times 1 over, and I can change the order downstairs. 16 plus x to the 4 is the same as x to the 4 plus 16. So this would be my first step. And then I will force factor a 16 out from the denominator. So I'll get x squared over 16 times 1 over 1 plus x to the 4 over 16, like this. All right, remember fractions are grouping symbols, so it's like this. And when you multiply this 16 distributed across here, you will get this. Now we're almost there. I have my x squared over 16 up front, and this piece I can write as 1 divided by 1 minus negative x to the 4 over 16. And here is your 1 over 1 minus r. Right, this right here is your r. This whole thing. So what you get then is that f of x is x squared over 16 times sigma n from 0 to infinity, negative x to the 4 over 16 to the n. Everybody see that? This is 1 over 1 minus r, where r is negative x to the 4 over 16. So this piece can be written like this. And then the x squared over 16 just comes along for the ride. We're not done. We're going to simplify this, and then we're going to push this shit into the series. So my next step is to simplify the stuff inside the series. The negative to the n is negative 1 to the n. Downstairs I have a 16 to the n. And then I have x to the 4 to the n, which is x to the 4n. And then I can bring the x squared over 16 into the series. I'll get sigma n from 0 to infinity, negative 1 to the n over 16 to the n times 16 is 16 to the n plus 1. And x to the 4n times x squared is x to the 4n plus 2. So that is your final answer. This is how we use the geometric series trick to come up with a series for pretty much any rational function. What we're going to do today is we're going to come up with series for things like this and then integrate them, or come up with a series for something like this and then differentiate it. So in order to really get going, I need to show you how to integrate and differentiate power series. Any questions on what we did here, or any one of these steps? We're all comfy with the algebra that gets us from here to here? Okay. So then, how do we integrate and how do we differentiate a power series? If capital F of x, and I'm using a capital F here just because it's a power series, is sigma n from 0 to infinity Cn times x minus a to the n, then the function is differentiable. In fact, more is true, but the fact that every power series is differentiable on its IOC and its derivative looks like this. So if you pay attention just to this part, if you differentiate just this part, it will become this, right? It's a power rule and chain rule thing. The power comes down, so this n comes down, and then you have x minus a to the n minus 1. You reduce the power by 1. And technically speaking, here we're multiplying by the derivative of the inside. The derivative of x minus a is just 1. The other thing you'll notice is that the starting index went from starting at n equals 0 to starting at n equals 1. This is because the constant term, the very first term of the original series, is a constant. It's just C0. That will differentiate to 0. The rule here, and I get asked this a lot, usually just before exam 3 or just before the final. The rule here is that you bump the starting index in this case from n equals 0 to n equals 1. Only if the original, this goddamn pen, has a constant term. Okay, I'm going to prove this theorem to you, so I'll be able to explain in a little bit more detail. But people always ask me, what's the rule? Do I need to bump the index or not? This is the rule. So that starting index, the n equals 0 down here, becomes an n equals 1 when we differentiate, only if the original series has a constant term, which this one and your fully general power series always do, but not every power series that we'll interact with does. So the purple rule here is important to remember. Make sure you get this in your notes along with this formula. All right. Also, capital F is integrable. Again, for x in the IOC.
What does it say after only if the what?
Only if the original series has a constant term.
Thank you.
So power series define differentiable functions everywhere they converge. And the derivative looks how you would think it looks. You differentiate it like it's a polynomial. You ignore everything except for this piece. When you differentiate this piece, just following the normal derivative rules from Calc 1, you get this. And then the only other catch is sometimes you bump the starting index from 0 to 1. When do you bump the starting index? Only if the original series has a constant term. So that's how you differentiate power series. And I'll prove this and show you examples. But before we finish the statement of the theorem here, not only are we interested in differentiating power series, we're also interested in integrating them. And it turns out that any function defined this way as a power series is automatically integrable, meaning you can integrate it for any x in the IOC. So if the series converges, you're allowed to integrate, and the integral, I'm doing an indefinite integral here, so we're going to have a plus c, and I'll write it out front. And then if you integrate this thing, just like when you differentiate, you only pay attention to this term. When you integrate, you only pay attention to this term. And there's no funny business with the starting index. So the Cn, the sigma, all that stuff just comes along for the ride. And then the integral of x minus a to the n is 1 over n plus 1 times x minus a to the n plus 1. Again, it's just power rule stuff, right? You can think of it as a tiny little u sub and a power rule thing. So these are the formulae for integrating and differentiating power series. I will prove these. We're going to let f of x be this series, the starting series, Cn times x minus a to the n, which remember is shorthand for C0 plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a cubed, and so on forever and ever. So if you jump in and just differentiate this one term at a time, then f primed of x is what you get by applying the operator d dx to this stuff. If I differentiate C0, this constant term, it will become 0. Derivative of a constant is 0. Plus, if I differentiate C1 times x minus a, the derivative of x minus a is just 1, so I get just C1. plus. If I differentiate C2 times x minus a squared, the derivative of x minus a squared is 2 times x minus a to the 1 times the derivative of x minus a, which is just 1. So the C2 comes along for the ride, and I'll get 2 times x minus a to the 1. Plus the C3 comes along for the ride, derivative of x minus a cubed is 3 times x minus a squared. And so on. These damn cats. Another kitty, figure out what you want. Right? So this piece differentiates to this. This piece differentiates to this. This piece differentiates to this. Just normal derivative rules applied to each piece on its own. Remember that all the C's are constants and that A is a constant. We're differentiating here with respect to X. So the n equals 0 term here goes away. And if I want to write this back in sigma notation, I'll have sigma n from 1 to infinity Cn times n times x minus a to the n minus 1. Look at it, right? 2 times x minus a to the 1. 3 times x minus a to the 2. The next term here would be C4 times 4x minus a to the 3. It's n x minus a to the n minus 1, which is the formula we get. So that's the proof of the first part. Also, the integral of f, that would be the integral of C0 plus C1 times x minus a plus C2 times x minus a squared. Is that a black cat or a white cat? Okay, good. Plus C3 times x minus a cubed and so on, done dx. And just like how we differentiated one term at a time, we're going to integrate all this shit one term at a time. The catch is, first I'm going to make a little substitution. I'm going to make the substitution z equals x minus a. dz is just dx. It's a simple little substitution. So this will become integral C0 plus C1z plus C2z squared plus C3z cubed, all done dz. I'm doing an indefinite integral, so I do get a big plus c, and I'll put it at the front. The integral of C0 dz is C0z. The integral of C1z is C1z squared over 2 plus the integral of C2z squared is C2z cubed over 3 plus the integral of C3z cubed is C3z to the 4 over 4 and so on. Now we go back to our original variable. That's C plus C0 times x minus a plus C1 over 2 times x minus a squared plus C2 over 3 times x minus a cubed plus C3 over 4 times x minus a to the 4 and so on. And I can collapse this back into the sigma summation notation. This is C plus, what is all this? sigma n from 0 to infinity, Cn times 1 over n plus 1, or Cn over n plus 1, times x minus a to the n plus 1. And that's the proof. So the two formulas that I gave you here, they work. That's all. We just proved that those formulas are correct. And this process of going through the proof is really useful. It's illustrative here because you'll be integrating and differentiating power series quite a bit. Not just in this class, but in differential equations and in physics. Believe it or not, even in certain statistics classes. All right. This is all well and good, but can we use it? My first and most favoritist example here is an integration example. I want to find this power series for the inverse tangent function. You guys know how much I love arctan. There's lots of good reasons to love arctan. One of them is that it has a very nice power series expansion. Focus, you fuck. Okay. So here's what I begin with. I know that the inverse tangent of x is the integral of 1 over 1 plus x squared dx. Yeah, there's a plus c, and I'm going to work that in a little bit later. But you know that when you integrate 1 over 1 plus x squared, you get arctan. I'll work the plus c down here. The reason this is useful is because I also know how to find a series for this. I can find a series for 1 over 1 plus x squared using my geometric series trick. So that's the roadmap here. I know that arctan is the integral of 1 over 1 plus x squared. I know how to find a series for 1 over 1 plus x squared. So I'll find a series for this, and then I will integrate it. That will give me the series for arctan. One over 1 plus x squared is 1 over 1 minus negative x squared is sigma n from 0 to infinity, negative x squared to the n. So let's start here. This is integral sigma n from 0 to infinity, negative x squared to the n dx. Now this series does not yet look like a regular power series. Before I can apply my formula to integrate, I need to rewrite this as a regular looking power series. In other words, I need to simplify inside first. That's sigma n from 0 to infinity, negative 1 to the n, x to the 2n dx. Now I can integrate. This piece is just going to come along for the ride. Capital sigma doesn't give a shit about the integral. You just have to integrate this piece. So you'll get constant plus sum n from 0 to infinity, -1 to the n. The power of x here will be x to the 2n plus 1. You just add 1 to the power, but you also need to divide by that power. This simplification step here, really important that you do that before trying to integrate. If you try to integrate straight from here, you'll mess it up. The formula doesn't work the same. In other words, you got to get it to some coefficients times a straight up power of x. None of this wonkiness. So for some constant c, we now know that the inverse tangent of x is equal to c plus the sum from 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n plus 1. And now we must find c. So if your task was just do this indefinite integral, then you would leave the plus c as a plus c. But here my task is to find a series for this particular function. This is not one function. This is many functions, right? Depending on what you plug in for c. These are all the vertical translates of this function. So I'm going to take this fact and I'm going to try to solve for c. The easiest way to do that is to write out this series, right? In the dot, dot, dot notation, get rid of the capital sigma, write it out, and then plug in a particular value of x. So I'll show you what I mean. Tan inverse of x is equal to capital C plus. Now, what are the first few terms of this series? Well, when n is 0, I get 1 over 1 times x to the 1. When n is 1, I get -1 over 3 times x cubed. When n is 2, I get 1 over 5 times x to the 5. And then 1/7, x to the 7, and so on. Now plug x equals 0. And you get that the inverse tangent of 0 is equal to c plus 0 minus 1/3 0 cubed plus 1/5 0 to the 5 minus 1/7 0 to the 7, and so on. This is definitely 0, as is this, right? Because it's 0 minus 0 plus 0 minus 0. It's all zeros. So 0 is equal to c plus 0. In other words, c here is 0. So the power series for the inverse tangent function you just take this formula and plug in c equals 0. So that c out front goes away. You get sigma n from 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n plus 1. This is something that you need to remember. Not just because I say so, and not just for this class, but forever and ever, amen. This is one of those hugely important results that you will use again and again and again. You will use it in Calc 2 here, but not just in this section. You will use it in Calc 3 and differential equations and physics, although Calc 3 maybe a little less so. Got to remember this. The other thing that you need to remember along with this is its interval of convergence. Now you could sort that out on your own using the ratio test. So I'm not going to burn class time on it. I'm just going to tell you that the IOC here is the closed interval -1 to 1. Okay. So this is what it looks like when you want to use integration to find a power series for some function. You have to begin with something you know. Here, I know that the function I'm trying to find a series for is the integral of 1 over 1 plus x squared. And then I find a series for the inside here. Then I simplify that series and integrate it. When you do this indefinite integral, you get this plus c. So the very last thing you have to do is sort out the value of c. The way we do that is by writing out the series. Never plug into the sigma notation here. If you go plugging 0 in here, you can get yourself in a lot of trouble. Take my word for it. All right, I promise. If you go plugging 0 in here, you can get yourself in a lot of trouble. So write the sum bitch out first. Okay, maybe you don't have to write the first 4 terms, maybe just the first 3, but write it out. Then plug in 0. Because this piece is not always 0. If you plug 0 into the sigma notation, it will definitely always look like 0. But this piece is not always 0. In this case, it was. So we were able to get that c equals 0 because arctan of 0 is 0. So 0 equals c plus 0. All right, that means c has to be 0. But the last kind of thing, I'll say it one more time, don't go plugging 0 into a series like this. Write it out first.
Are you always plugging in 0 for x?
Usually. You're gonna, so plugging like 1 in here or 1/2 or something else like that, you're not gonna be able to say what that is right away. All right, when I look at this, I'm able to go, oh yeah, that's definitely 0 because every single term of the series is 0. Usually what you'll be doing is plugging in whatever the center is. So this series is centered at 0. And so plugging in the center makes all the terms 0. Also, I happen to know what the inverse tangent of 0 is. So 0 is a nice number to plug in to this expression because I know the value of every single piece of this expression at x equals 0. But if I knew the value of every single piece of this expression at x equals 1, I could have done that also. But usually you'll be plugging in 0. Okay, so that's finding a series using integration. We will do one more example of this before the day is over, but before that, I want to show you how to use differentiation to find a series. Your homework this week will have a few problems that require you to use differentiation to find a series. And for some reason, these tend to be trickier. So let's take a look. So I want to find a power series for 1 over 1 minus x all squared. Just to be clear, this is not the same as 1 over 1 minus x squared like this, right? Just a note. Those are very different. It's not just the x that's being squared, it's the whole denominator. Foiling this out downstairs won't help us find a series. But when I look at that, 1 over 1 minus x all squared looks to me like the derivative of 1 over 1 minus x. So I'm going to use differentiation here because the function I want a series for looks to me like the derivative of something else. Think about the power rule. This is 1 minus x to the negative 1. If you differentiate that, you get 1 minus x to the negative 2, or something very close to it. You should check your guess. So if I go ahead and take the derivative of 1 over 1 minus x, do I actually get that? Well, that's the derivative of 1 minus x to the negative first power. So I will get a negative 1 times 1 minus x to the negative 2. And then by the chain rule, I have to multiply by the derivative of the inside, which is negative 1 again. So the two negative 1's become positive, and we do get 1 over 1 minus x squared. If your guess was off by a little bit, like if I didn't get another negative here to get rid of this, then I would have to go back and change my guess. But this turns out to be correct. So now, just like last time where I said the thing I want is equal to some calculus operation applied to a thing I know how to find a series for, I will find a series for this, then differentiate that series. That will be the series for my function. People get in trouble here because a lot of times they don't want to make this guess. They want to know for sure what this is the derivative of, and the sure way to do that is to integrate this. That works, but it has this nasty counter effect of making you forget what it is you're trying to do. Are you trying to differentiate a series or are you trying to integrate a series? So my recommendation, and this is the only place in all of the classes I teach I will ever use the words guess and check that close to one another in a sentence. My recommendation really is to take a guess at what your function is the derivative of. Basically, you're doing an integral in your head, but don't write down the integral. You'll get confused. Take a guess and then modify it if you need to. So we've verified that this guess is correct. So the function I want a series for, I know is the derivative of this function that I know how to get a series for. 1 over 1 minus x, that is your straight up simple geometric series, sigma n from 0 to infinity x to the n. I need to ask, does this have a constant term? Right, because I'm wondering, do I need to bump the index when I differentiate? So let's write out the first few terms of that series. When n is 0, you get x to the 0, which is 1, plus when n is 1, you get x to the 1, plus when n is 2, you get x squared, plus when n is 3, you get x cubed. So does it have a constant term? Yes. Right, the 1. And that term is going to differentiate to 0 because it's a constant. So yes, we bump the index. We'll bump n equals 0 to n equals 1 when we differentiate. All right, let's go ahead and take our derivative. My original series does have a constant term, so the starting index n equals 0 gets bumped up to the starting index n equals 1. Then the derivative of x to the n is n x to the n minus 1. That's it. So that's your series. And you're done. Questions on this example? Okay. You probably noticed last week as you were working on the homework that all of your answers have the capital sigma written for you. And a lot of the times they have the starting index set for you. You don't get to choose it as 0. So if I wanted to rewrite this as sigma n from 0 to infinity of something, I would do that by writing out the terms and then trying to collapse back into sigma notation. So when n is 1, I get 1 times x to the 1 minus 1, which is just 1. When n is 2, I get 2 times x. When n is 3, I get 3 times x squared. When n is 4, I get 4 times x cubed, and so on. So if I wanted to write this as sigma n from 0 to infinity of something, what would that look like? Well, 1 is 0 plus 1, so maybe an n plus 1 here. And then the powers of x ascend, they're just 1 less than that. So if I had to write this as a sum from 0 to infinity, this is how I would write it. And I get there just by writing this thing out and asking how can I write that as sigma n from 0 to infinity. There is also an algebraic way to do this. You notice that this n became an n plus 1, that this n minus 1 became an n. So the n's in the series bumped up by 1, and that lets me bump the index back down if you want to. If you want to start at n equals 0, you can, but you have to adjust the series. On an exam, I would prefer it like this, honestly. In most settings, this is great. This is the way to go. But sometimes in your homework, they'll ask you to make the series start at 0. So you need to do this transformation. And the easiest way to do it is just write it out. Just write it out and then look and see how you could make that as a sigma n from 0 to infinity. I want to do one more integration example if there are not any questions on this, but first I really do want to make sure we've taken care of any questions on this. So questions on this?
No, but can you give me 1 second? Gotta finish writing this down.
Sure, of course. We'll zoom out just a smidge.
Got it. Thank you.
You're welcome. Okay. So one more integration example, and then I want to talk about what integrating and differentiating do to the IOC. So here I want to find a power series for the natural log of 1 plus x. Is there any function I know that has this as its derivative? Not a rhetorical question, I really want an answer. Any function that I can differentiate to get this, that you know right away. That's the derivative of this, but if you differentiate 1 over 1 plus x, you don't get the natural log. So Nathaniel's answer is kind of what I'm looking for. There is nobody I know right away who differentiates to this, but I do know a function that integrates to this. I know that the natural log of 1 plus x is the integral of 1 over 1 plus x. All right, it's a tiny little u sub. You u sub for 1 plus x, you get integral 1 over u du. That is natural log u, which is natural log 1 plus x. So this is my jumping off point. There's a plus c, but we'll slap that on later. So in order to find the series for natural log 1 plus x, I will find the series for this and then integrate it. 1 over 1 plus x is 1 over 1 minus negative x. Which is sigma n equals 0 to infinity negative x to the n by my geometric series trick. And then before I can integrate, I need to simplify the series. That's sigma n from 0 to infinity negative 1 to the n times x to the n dx. And now, according to my integration rule for series, this is going to be c plus sigma n from 0 to infinity negative 1 to the n over n plus 1 times x to the n plus 1. And just like in the first integration example, to proceed from here, I need to find the value of the constant c. Hey, ball. Hey, good boy. It's okay. Just like in the previous example with arctan, the way we're going to do this is by writing natural log of 1 plus x equals c plus, and then I write out the first two terms of this series. When n is 0, I get 1 over 1 times x to the 1. When n is 1, I get minus 1/2 x squared. When n is 2, I get plus 1/3 x cubed. When n is 3, I get minus 1/4 x to the 4, and it goes on and on like that. And if you plug x equals 0 on both sides here, you get the natural log of 1 equals c plus all of these with zeros plugged in, that's 0, right? It's 0 minus 1/2 times 0 squared plus 1/3 times 0 cubed minus 1/4 times 0 to the 4, and so on. The natural log of 1 is 0, so you get 0 equals c plus 0, which means c must itself be 0. Therefore, the natural log of 1 plus x can be written as sigma, right? C is 0, so it's just sigma n from 0 to infinity, negative 1 to the n over n plus 1 times x to the n plus 1. And this is another one of your kind of holy power series. Store this somewhere safe in your memory where it will never be forgotten. It is special. Just like the other special series we learned, we should remember along with it its interval of convergence. The IOC here, I have to think about this for just a second. If I plug in -1, that will diverge. If I plug in +1, that will converge. So this is left open, right closed, -1. So we learned two new very special power series today. The power series for the inverse tangent function and the power series for the natural log function. Before I move on, and there are lots of fun things we can do with these, I'm going to do two examples here at the end. I want to talk to you a little bit about intervals of convergence and the process of integrating and differentiating. Before I do that, are there any questions on this example? Yeah, I got you. Here we go. Again, to go from this step to this step, I'm using the geometric series trick. So this step I used the fact that 1 over 1 minus r is sigma n from 0 to infinity r to the n. And that lets me replace this by this. All right, I'll leave it here for just a second longer. Folks who are still writing, I know there's a lot to get down. Anything here that we would like to talk about? Anything that feels odd or anything that you just want to comment on? All right, moving on in 5, 4, 3. Here we go. What I'm about to show you is a theorem. And if you look in your textbook, you won't find this in the online homework because it's not a problem that translates into WebAssign stuff very well. But if you look in your textbook, it's actually the very first problem in section 11.9. So it's not a hard theorem to prove. If capital F of X is the power series sigma n from 0 to infinity Cn times x minus a to the n has radius of convergence capital R, then so do the integral of f, which remember is c plus sigma n from 0 to infinity Cn times 1 over n plus 1 times x minus a to the n plus 1, and the derivative, which is sigma n from 1 to infinity Cn times n times x minus a to the n minus 1. In other words, this theorem says integrating and differentiating do not change the radius of convergence. However, the interval of convergence can change. I know that's not a correct use of the apostrophe, but it just makes it read better. The IOCs can change according to the following rules. Integration may pick up one or both endpoints, and differentiation may lose one or both endpoints. So if you integrate a series, the radius of convergence won't change, but you might gain an endpoint. So maybe you integrate a series that has an open IOC. You might get a series that has a closed IOC, or maybe half open, half closed. If you differentiate a series that has a closed IOC, you may lose one or both of those endpoints. The size of the IOC won't change, but you can pick up or lose an endpoint. We've actually seen an example of this already. The series 1 over 1 plus x squared. This guy, remember, has power series sigma n from 0 to infinity, negative 1 to the n, x to the 2n. This has IOC open from negative 1 to 1. But its integral the inverse tangent of x, which we've seen has power series sigma n from 0 to infinity, -1 to the n over 2n plus 1, x to the 2n plus 1, has a closed IOC. So when we integrated this to get this, the radius of convergence didn't change. The radius of convergence is 1 for both of them. But that process of integration actually picked up both endpoints. The original IOC didn't contain either endpoint. After we integrate, the IOC contained both endpoints. And if you read this in the other direction, this guy contains both endpoints, but his derivative contains neither. You can also think about this in terms of the log series. ln of 1 plus x, which we said has power series sigma n from 0 to infinity, -1 to the n over n plus 1 times x to the n plus 1, has IOC. I gotta be careful here. If I plug in 1, it will converge. If I put in -1, it will diverge. Has this as its IOC. But its derivative which is 1 over 1 plus x having series sigma n from 0 to infinity, -1 to the n, x to the n, has IOC open -1 to 1. So if you differentiate this series, you lose the endpoint +1. It gets kicked out. And if you integrate this series, you gain both endpoints. So integration, you can gain an endpoint or two. Differentiation, you can lose an endpoint or two. And in neither case will you change the radius of convergence. Integration and differentiation do not change the radius of convergence. The proof of the theorem, like I said, is not hard. And I want you to do it. These are problems 1 and 2 in section 11.9. You haven't seen them yet because last week I split the homework into 2 pieces because you didn't have a full week. So rather than doing all of 11.9 last week, I kept all the calculus stuff out. But this week I want you to look at these problems, even though they're not in WebAssign. Let me show you. Moving to the textbook. 11.9. If the radius of the power series Cn x to the n is 10, what's the radius of convergence for this series? Well, this series is the derivative of this series. And what you're going to discover when you solve this problem is that the radius of convergence of the new series is also 10. Why? Use the ratio test. Similarly, problem 2 says, suppose you know that the original series converges for all absolute value of x less than 2. This series is centered at 0. So this is the same as saying that the interval of convergence for this series is the open interval from -2 to 2. What can you say about this series, which is the integral of this series? Right? Add 1 to the power, divide by the power. The series down here is the integral of this series. And we want to see if you can find the radius and interval of convergence of this series. You won't be able to say what happens at the endpoints for sure, but you will be able to say that the radius of convergence is the same. And that's our theorem here. So I would like you to prove this theorem. Think of it as an extra exercise. People are always asking me, what can I do to do better on the next test? Here's an example of something you can do to do better on the next test. Prove this theorem. How do you prove it? So the proof here is a bonus exercise. For you, use the ratio test. The hint here is that L is the same for the original, integral, and derivative. Right, so I claim that the limit L you get from the ratio test is the same for all three, for the original series, for the integrated series, and for the differentiated series. All of those will get the same number L for the ratio test, which means they all have the same radius of convergence. So see if you can compute L for the original series, for the integrated series, and for the differentiated series. See if you can show that you get the same thing for all three. And then be aware that when you integrate, even though the radius of convergence will never change, sometimes you'll add an endpoint or two. And be aware that even though the radius of convergence won't change, sometimes you may lose an endpoint or two when you differentiate. And these examples from series that we found today in class are really good kind of characteristic examples to keep in mind. Any questions on this theorem or these examples or what I'm asking you to do here? All right. Then I've got a couple little things I want to show you before I let you go. We may go just a little bit over time here. I really appreciate it if you can stick around because there will be homework problems relevant to this, and I don't want to burn class time on it tomorrow because it's simple and fast. Suppose I ask you to find a power series for the function f of x equals maybe x cubed times the inverse tangent of x squared or something like that. You don't need to start all the way at the beginning because you know that the inverse tangent of x has the following power series. So if I swap the x for an x squared, that will give me this piece. Which I can simplify. If I take x squared and I raise it to the 2n plus 1 power, I just multiply the powers. So that would be 4n plus 2. And now I can multiply everything by x cubed. So x cubed times arctan of x squared would be x cubed times this series. And I can move this x cubed inside the series. X to the 4n plus 2 times x cubed is x to the 4n plus 5. So I'll get sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 times x raised to the 4n plus 5. Very fast, right? No need to go back to the kind of ground level work, because I know the series for arctan. I can plug x squared into that to give me a series for arctan of x squared. And then I can multiply that whole thing by x cubed to get the series I want. Similarly, I could find a series for like any sort of natural log thing. Yeah, that happens. I have gone through, I think, 5 reams of paper so far this semester. I think that's about 1,000 sheets. It's crazy how much paper we can go through, especially in this class. Okay, one last example. Find a series for ln of, what do we have? We've got 1 plus x, right? Let's do a series for ln of 2 plus x. Again, here I know that ln of 1 plus x has power series sigma n from 0 to infinity, negative 1 to the n over n plus 1 times x to the n plus 1. So I'll be using that. And then I say, okay, well, the ln of 2 plus x is the ln of 2 times 1 plus x over 2, kind of similar to the force factoring we did with our geometric series trick. Then I can use properties of the logarithm to say, okay, well, this is ln2 plus ln 1 plus x. Son of a bitch, come on, x over 2. The ln2 piece is just going to come along for the ride, and this I can now get by substituting into here. So this is the natural log of 2 plus sigma n from 0 to infinity, negative 1 to the n over n plus 1 times x over 2 to the n plus 1. And we can simplify this piece. This is negative 1 to the n over n plus 1 times 1 over 2 to the n plus 1 times x to the n plus 1. So oftentimes, when you're coming up with a series for a function, you don't need to start at ground level. You can think about how this compares to something else we already know the series for. And if you're lucky, you can do some amount of algebra and then plug in to get your new series as a consequence of the old series. And these are two kind of classic examples. This is a technique we will use a lot, like a lot. All right. So that is everything I wanted to go through today, and that finishes up section 11.9. Your homework this week will have 11.9 and 11.10 problems. 11.10, section 11.10, we're going to start talking about on Wednesday. That's about Taylor's theorem. Taylor's theorem is a very formula-heavy section. Some people find it intimidating, so you probably want to read it ahead of time. All right, so between now and next Wednesday, I'd like you to do the following things. Prove the theorem I asked you to prove, the bonus exercise. which are problems 1 and 2 from your textbook in section 11.9. I can't assign them on WebAssign. They just don't work in WebAssign because you can't ask students to write a proof in WebAssign. It just doesn't work. But open up your textbook, whether it's physical or electronic, solve problems 1 and 2 from section 11.9. Then do the homework and then read section 11.10. Oh shit, no, we fucking don't. It's Veterans Day, isn't it? All right, well then on Friday, on Friday we will discuss Taylor's theorem, which means it's going to be a slightly compressed class. So definitely read section 11.10. All right, I'll say it one more time. Read section 11.10. I'll show you something really quick here, just how much alphabet soup there is. All right. This is them deriving Taylor's formula. This is Taylor's formula. This is Taylor's formula. Looks a little bit scary. There's some n factorials. You may not even know what this notation upstairs here means. This is the nth derivative of f evaluated at the input a. So please read this section, yeah? Solve problems 1 and 2 from 11.9, then get started on the homework, then read section 11.10, all right? We're gonna get power series for e to the x. We're gonna get power series for sine and cosine. We're gonna get power series for your arbitrary binomial expansion, meaning like 1 over the square root of x plus 5, that sort of stuff. We're gonna get lots and lots of really important things here. They're all gonna follow from that very complicated looking formula. And then we're going to start talking about applications. So please solve problems 1 and 2 from section 11.9, then get started on the homework, then read section 11.10. All right, read this before class on Friday. Have I said it enough times? All right, that's it. Okay, that is it. I will have your exam grades in by the end of the day today, I promise. And then study guide grades will follow after that. But I've got some other classes that want test grades, so I will be doing those before study guides. Expect study guides by Thursday, exams by today. If you have any questions, you need to talk to me. You can always come see me in office hours. I have an office hour today from 3:30 to 4:30. Otherwise, as is always the case, you can send me a Canvas message or an email and I'll get back to you right away. Okay, that is it for today, guys. Have a good day.